All right, welcome back. Topic 10, motor skills, subtopic 10.5, predictive models of movement time. So 10.4 was about predictive models of reaction time, how fast until humans initiate a movement. And now this subsection here talks about modeling the amount of time it takes to complete a movement, to reposition a limb in order to interact with a control, for example. So reaction time right here, that's what we calculated in 10.4. Today we're talking about 10.5 movement time, and the sum of these two together are going to give us this overall response time, and that's ultimately the what we need to know for the amount of time between when a human is when the senses of a human are able to pick up a stimulus, right, until they can initiate something through a control interaction to affect the system. So the time between brake light and step on brake is response time here. So again, 10.5, we're talking about movement time, okay? So MT, to distinguish from RT, and this would be defined from, again, here, let me go back, that moment that the movement is first initiated. So the second that the first muscle fiber fires to lift the foot off of the accelerator, and then until that foot has moved over and not has fully depressed the pedal, but has contacted the pedal, okay? Then we can talk about how long it takes to fully depress the pedal. That's a different, that's an add-on as well. But the time from brake lights to ready to initiate, or basically initiating a control input is our response time. So, right, so movement time is characterized by a speed accuracy trade-off, meaning you can either be faster or more accurate, but you can't do both of those. And so, this example, I always go to video games. This is a Mario Party game where you're tracing these shapes as quickly as you can, but need to be accurate enough that you cover the path. And so, of course, if I go really, really fast, it's not going to be accurate. I'm not going to advance. If I go too slow, I could be accurate enough, but I'm not, winning the race. So that's the challenge. That's the trade-off we're dealing with. And just like we had the Hick-Hyman law for reaction time, we have a law in a set of tasks that go with it for movement time, and those are attributed to Paul Fitts. So Fitz's law, let me be careful each time I say that Dr. Fitts has an S at the end of his name, and then possessive adds another apostrophe S. So Fitz's law describes this trade-off, the speed accuracy trade-off. And ultimately, if you tell somebody you need to be at least this accurate, you can model the amount of time that it takes to perform a movement according to that accuracy. And then this sort of model could then be applied to designs of control layouts, so how far do I need to move my arm to reach a control or to interact with a control? That is going to affect movement time. That's going to affect how quickly I can respond in a given system. All right. So this is a older now schematic of what is usually used to study this phenomenon, which is that speed accuracy trade-off. If I'm doing an accuracy task like contacting a certain target and I have to quickly do that, then they're basically one of the ways to study that and to get lots and lots of data points is to have this sort of a setup. So obviously this is top down here. This is the human holding a stylus, but it doesn't have to be it could be a finger, could be a fist. It's anything where you're contacting a target with something. And basically it's, to collect a lot of data quickly, there might be, hey, tap here, tap here, tap here, do this as quickly as you can, back and forth for 20 seconds, and these are maybe different target locations, tap the black target, tap the red target. And these would be characterized by a certain reaching distance, and then also the width of the target. So essentially the size of the target in the direction that I'm moving. So if I'm going tap, 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 tap as quickly as I can, Fitts' law can help predict what the amount of time to complete those movements would be. Key here is that you emphasize accuracy rather than speed. It's not speed or accuracy, it's you need to achieve a certain degree of accuracy, meaning you need to land inside the target. Close to the target doesn't count, inside the target boundaries, and to do so as quickly as you can. So this is, another example, and illustrating those two variables, right? So we're going to get faster movement. So this is a movement time predictive model. That movement is faster, meaning, it takes less movement time, shorter amounts of time, if the target amplitude is smaller. So if the targets are closer together, it's faster, right? And if the target width is larger, so it's an easier target to hit, I can slap at it a little bit more easily. I don't have to slow down and be precise, right? All right, so Fitz's law. So we call this tap, you can call it the tapping task. I have seen it called Fitz's task. I'm going to call it Fitz's law task. And the reason that's goofy to me, and I wish I had a better, way to phrase it, is I've written proposals where I've specifically, addressed this, and in particular, actually addressed this. So now, Fitz's law works for a two-dimensional sort of control, but a lot of what we're interested in now is, mappable in three-dimensional space. So as long as I can define how far I have to reach and what is the range, sort of the, acceptable size of the target I'm trying to contact, you can model it according to Fitz's law. Right. Okay. Good. Okay. Yep. So here's another example, 3D version of it. So again, you just need to know what is the size of the target and how far away is it. The target amplitude is how far do you have to move. All right, so here's the math side of it, right? So just like Hick-Hyman, in fact, we have that, there we go. We have a linear relationship between how complicated, how much thinking time is needed, and how long it takes, to complete a movement. So we have A, which is A and B are both constants, and ID stands for the index of difficulty. And so this is going to have some logarithm in here. I'll show you on the next slide or so. But just think of this as how complicated the motor program is. So before, you've got your motor cortex here in the brain. It is generating the motor program. You've loaded that cartridge motor program like I talk about, and you click go. And now the index of difficulty is essentially, think of it like the number of operations that might need to be run in that program, the complexity of the movement, right? So, moving my arm out like that is not very complex. Doing a sweet dance move is complex. That would have a higher index of difficulty, okay? A and B are empirically derived, just like with Hick-Hyman, those are also empirically derived. But in this case, we can again sort of see a relationship between what these values tend to be empirically and some physiological factors like the speed limit of neural conduction, for example. So A and B depend on the body segments performing the movement and basically the neuromuscular latency. So my brain has a fundamental, it's going to take this long to start sending a signal. And then if I'm sending a signal to my arm, that actually gets there faster than if I send it to my leg. It's got a longer neural distance to travel. It takes a little bit longer. So that's why the body segments matter for this calculation. But neuromuscular latency, this is kind of like that fundamental speed limit of neural transduction comes into play here, right? So it's only part of it, neuromuscular latency. There's some, the signal has been received at my muscle and it's starting to contract. All of that goes in, from the message being sent to the start of the contraction. That'll be neuromuscular latency. All right. So again, index of difficulty, ID. This is calculated again by recognizing that this is an easier movement if you move not as far. So D, that's our distance between targets. And if the target is larger in size, so I don't have to be as precise in my movements, and that'd be W. W is the width of our target in the direction of motion, right? So the way that this is, illustrated here, W is only if I'm moving in this dimension, right? If these are targets and I'm moving in a lateral dimension, or sorry, up and down dimension, then W would be the height of this target. So it's in the dimension that you're moving, the width of the target. All right, in the direction of motion. I've highlighted this, I've added some color to it to not forget that there's actually a 2 in here. So it's a factor of 2 times the ratio of that distance to the width. I want to say that has something to do with there being 2 targets, but I don't exactly remember how the 2 comes into play. Just make sure you include it. We're also using log base 2 because we are calculating the difficulty in bits. So it very much works, really, really in parallel, like with the Hick-Hyman law, where you had, the amount of information that had to be processed before there was a reaction. Now you have the amount of information that's processed as part of the movement, the motor program. All right, and again, the index of difficulty is higher, meaning there's more bits when there is a longer distance and when there are smaller targets, so you have to be more precise. And again, think of this like the complexity of the motor program that has to be loaded, in that cartridge, as you're about to initiate it. All right, there we go. So if we plug in that log base 2, if we plug in that calculation for index of difficulty, this is what our movement time equation gives us. Neuromuscular latency, and again, for this class, you can always use the same constant here, is always going to be 0.1 seconds, 100 milliseconds. Universal constant, we're just going to use that. Just know that that was empirically derived at some point, and if you're going to be using very precise sorts of measurements, you probably want to re-empirically calculate that to be sure that it's accurate for whatever task you're doing. And then note that, again, if I'm sending a signal to my hands, it's faster than to send it to my legs, so that has a noticeable difference. And I don't think you can always say it's exactly because of how far from the brain. There's some aspects of processing in the arms and legs that just take different amounts of time. But if it's a hand-based movement, I want you to use this constant, 0.12 seconds per bit. If it's a foot, 0.18 seconds per bit. So don't forget this. I may very well give you a problem in your homework that depends on knowing, am I moving the hand or am I moving the foot? Make sure you use the right constant. All right, thanks. Okay, so we can calculate movement time now. Now we have our equation, and we also have our equation for reaction time. So let's see if we can figure out overall response time. Let's go back to our skunk from topic 10.4. So now I want to say, okay, I know how long it's going to take me to react to the skunk in the road, meaning I see that there's a skunk. I now have decided what I'm going to do, whether that's, swerve left or right, speed up, slow down, whatever that is. Remember, we calculated that in 10.4. And so if we get 0.37 seconds is our reaction time, based on how we had set up the problem in 10.4, now we can say, well, what's my movement time? Okay, so I got to add that to the reaction time to get the overall time to reach the brakes, right? So, all right, A plus B times our index of difficulty. We're going to use the constants that I just introduced. A is 0.10. I am using my foot to do this control movement, right? So it's going from gas to brake. So I'm going to use this 0.18 seconds per bit a constant. If it were my hand, make sure you're using the hand one, right? Good. Make sure. Our distance and our distance from pedal to brake, throttle to brake, and the width of that brake pedal. I'm just going to give you some numbers here, right? I'm just making these up, but you can see that they kind of make sense. 8 inches and about 5 inches in width. Now, note, this is from the center of the throttle to the center of the brake. So you're assuming that people are aiming for the center of the brake. You can make other assumptions there, but you have to assume what you're predicting here is somebody aiming for the center of something, but having enough leeway that they don't have to focus too much to make sure it's in the dead center. Okay, but it's not like I'm going only a few, like 3 inches over, right? The 5 inches is the width of this, but it's 8 inches to the center from pedal to pedal. All right. So we can plug these in now, put them all into our movement time equation. We get 0.40 seconds. Again, don't forget to multiply by 2, that 2 times the distance. Don't forget it, very key. And so 0.40 seconds. Now, if we add that, so if we say the overall time to reach the break, the response time, which is reaction time plus movement time, we get 0.77 seconds. Okay, so 3/4 of a second is how long it takes. Now, does this make sense? I crest the hill. I see that there's a skunk. I decide I'm going to brake. 0.75 seconds later, I have my foot on the brake ready to depress. Okay, I think that makes sense. That's a good timeline. And check this out. So we just predicted, we just made up a bunch of numbers and said, well, what would it, about how long would it take? 0.77 seconds. And then I compared that with the design standard, which is used by, the American Association of State Highway and Transportation Officials. So, the folks that say, here, this should have a different speed limit for this reason. And their model estimates, the amount of time that it takes between seeing something and deciding what you're going to do and initiating that response, or the perception reaction time, as they call it, is 0.75 seconds. So very similar to what we just calculated with our predictive models using Hick-Hyman and Fitz's law. All right, so we're still talking about movement time. There is another way to think about movement. So Fitz's law, you remember in 10.2, we talked about open loop and closed loop movements. Fitz's law works for closed loop movements. It's much more, applicable there because there's a lot more processing the information as it's being received and having that guide the activity. In open loop sorts of activities, you're basically just kind of letting it go, right? So remember, I'm throwing a football or I'm throwing a baseball. I don't have time to react to my surroundings and adjust my motor program. I'm basically loaded the cartridge and said execute, right? So for this more open loop, or sometimes referred to as a ballistic movement, think of this as like, I'm just gonna slap at something. It's a really big target or it's not very far away, such that if the index of difficulty is less than 3 bits. So I say like, hey, this child who's, slapping from drum to drum, I would say that's probably less than 3 bits. And it's the kind of movement where you don't really have to aim. You can just kind of slap, 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 slap. So if you kind of think about like, I'm just flailing at something, that's sort of to me like, okay, that's going to have a different model than the I'm doing a calculated movement to contact something. So that fits into this world of ballistic or open loop movement. So the approximation here is we've got 2 different constants. So we had A and B times the index of difficulty. Now we have E plus F, and a different way that we're essentially calculating how many bits of information are processed in this movement. And it's the square root of the distance. So if we can calculate from our index of difficulty metric, log base 2 times distance divided by width, if that's less than 3 bits, then people aren't really aiming and they're more flailing, okay? And when they flail, this is a better approximation, than the full index of difficulty equation. So again, this is a modified variation of Fitz's law. Note that when I have you do your homework, I will state, do not do the variation of Fitz's law, because I want you to stay with the formal version of it. Just realize for the real world, this is something you probably want to know about. Don't just, always use the same version of that law. All right. So, how would this look differently if we go back to our skunk example? So I'm not really aiming when I move my foot to the brake pedal. I'm familiar enough that I can kind of just, flail my foot over, so to speak, or very much, I don't need to, it's a open loop movement in that I am throwing my foot at the brake as fast as I can. I'm not aiming for that control. So now index of difficulty, 2 times 8 inches was our distance, 5 was the width, 1.678. So I would say, yeah, that is fewer than 3 bits, and therefore the ballistic approximation can be used. So I know it's E plus F square root of D. Now, I don't know what E or F are yet, and here's where it gets really important to collect your own data to be able to figure out what those are. So to calculate E and F, let's imagine we did this. So let's just pretend I got somebody in our driving simulator, and I measured that distance, you know, and I said, okay, at any point that you might see, you know, this skunk or something, I want you to move your foot over, or, you know, when I tell you to move your foot over, and we're going to measure how long it takes, you know, for you to get to the brake. And so we collect these data, and we find out that, hey, if we set the brake and the pedal, you know, 8 inches apart, the movement time is 0.77. If we move it 12 inches apart, so we move it further, it's 0.83. This gives us 2 equations, 2 unknowns, and so we can solve for E and F this way. And that might give us these 2 values. And so I hope you can follow my math here. I'm just solving for E and F with these 2 equations. And then I could say, well, what if the pedal is 10 inches away? What would a ballistic approximation do in terms of movement time? Well, I'm going to use the same 2 constants I just empirically derived. I plug them in. I use my square root of D as our index of difficulty replacement. I get 0.80 seconds. So again, this is within the same range, the same ballpark that we've been talking about, but maybe a little more representative of these sorts of, I'm just going to foil at it sorts of movements, as opposed to I'm going to have a precise aimed motion. All right, that is 10.5.